Good day and welcome to our talk on using specification of overburden to improve numerical longshore sediment transport modeling. This is Irene Watts and my co-author is Gary Zarillo. This work was performed at the Florida Institute of Technology, located in Melbourne, Florida, in the United States. It is supported by the Sebastian Inlet District and monitoring array supported by Sakura. Thank you for your interest in this work. The Coastal Processes Research Group at Florida Tech have been partnering with the Sebastian Inlet District for over 10 years, and we've been supporting sediment management activities through the use of coastal process modeling. A list of some research efforts and investigations are listed on the left-hand side of the panel. Previous studies include evaluating a variety of structural alternatives to address erosion concerns on an interior beach, and investigating hydrodynamic conditions that encourage sand backpassing into the inlet. The work that I will be covering today is focused on incorporating domain-wide overburden to improve longshore sediment transport computations. The roadmap of elements that I will be covering today include the motivation of this work, present a brief site characterization for context, present the modeling approach and methods used for this work, provide interpretation of results, and present conclusions and potential implications for numerical modeling. The motivation of this work, we seek to improve the application of a coastal process model in a unique and challenging environment. This tool is used to support sediment management activities at this tidal inlet. Activities include routine dredging of an interior sand draft and downdrift placement. Also on site is a DMMA that is used in rapid storm response. Hard bottom outcrops are present throughout the study domain and are important for computing longshore sediment transport and morphology change. Hard bottom outcrop locations are known and well represented in the model. The goal of this work was to improve our longshore sediment transport calculations domain-wide to support additional decision-making of sand management. I'll present a brief site overview for us. The Sebastian Inlet is located on the Atlantic coast of Florida, just south of Cape Canaveral and north of Miami. The inlet is one of the few connections between the interior Indian River Lagoon and the Atlantic Ocean. This inlet supports the local fishing community and is a popular tourist destination for camping and surfing. The inlet itself is part of the Florida State Park system. From a morphological standpoint, this inlet has well-defined flood and ebb shoals along with channel linear marginal bars. Hard bottom rock outcrops are visible in the aerial imagery. An example is located here just south of the inlet. The hard bottom rock outcrops are mapped using both aerial imagery as well as previous field investigations. Eelgrass is also present on the flood shoal and are routinely monitored. These eelgrasses provide an important habitat. The site has a comprehensive monitoring array and ongoing field activities that support the modeling efforts. This array provides field data both north and south of the inlet and spans approximately 5 kilometers alongshore. This monitoring array consists of 6 bottom-mounted ADCPs that are capable of directional waves. Existing ADCP locations sited just north of the inlet has been maintained for about 20 years. This particular node consists of 2 co-located gauges. One is real-time cabled to a shore station and a second is autonomous for backup purposes. There is also a MET tower located at the distal end of the north jetty with a standard meteorological package. A radar-based water level gauge is also located on the north jetty and is referenced to the vertical datum. Biannual bathy and topo surveys are also performed, which include multi-beam from the inlet southwards and single beam for the rest of the study area. These surveys also resolve the dune line. A complete sediment characterization has supported research into both carbonate and multigrain sediment transport studies. We have a complete sediment characterization at this site, which includes samples along the entire model domain and including both the flood and ebb shoals. Carbonates arise in this area from weathering of exposed coquina, which is part of the Anastasia Formation. The biggest take-home from this slide is being aware of the large percentage of carbonate material and that this platy material is present at all grain sizes in varying quantities. I have some other work coming out that will address the implications of this material and provide guidance on its incorporation into this model and others. The model used for this work is the coastal modeling system and consists of a wave model and flow model which runs implicitly in line. Processes included in this model and general workflow is diagrammed in the left panel. We are using a nested grid configuration with a regional grid that brings waves in from the offshore areas from a wave watch lead location to the local grid. The regional grid consists of approximately 70,000 computational cells within a longshore distance of 18 kilometers and a cross-shore span of 40 kilometers, extending to water depths of 40 meters. The local grid uses a quad-tree telescoping grid approach and spans 18 kilometers alongshore, 10.5 kilometers offshore, to a water depth of 17 meters. Hard bottom and overburden specification is performed in the local refined grid. The flow grid contains nearly 300,000 computational cells ranging from 5 meters by 5 meters nearest the inlet to 160 meters by 160 meters in the offshore areas. The model is run on a PC and generally takes about 5 days for a 6-month simulation depending on the various processes that are included. The telescoping grid is using a longshore uniform refinement which we have found to best support nearshore processes both from a longshore sediment transport standpoint and morphology calculations. Additional refinement was added to the nearshore areas to maintain uniform refinement alongshore out to the depth of closure. This increased model stability and further resolved longshore sediment transport computations. The model experiment design was straightforward to evaluate the performance differences between specifying known hard bottom outcrops with the domain-wide specification of overburden. Spatially varying unimodal grain size is used for both model alternatives, and the model runs are bounded temporally by field surveys. We have strong hydrodynamic model skill at the north ADCP location, and sediment computations are performed using the Longshore formulation using the net total volume approach. The method of calculation of longshore sediment transport is performed by the construction of a series of alongshore observational arcs that extends beyond the depths of closure within the same model grid refinement level. The spacing of these arcs is approximately 300 meters. Calculated longshore sediment transport is compared with measured using the same arcs for continuity. The equation of total load sediment transport rate is pictured here in the center of the slide, where Q is the total load sediment transport rate vector, T is time, L is the length of the observational arc, and N is the unit vector normal to the observational arc. The plot on the right panel displays the measured and computed longshore sediment transport rates. North is at the top of the image and south is at the bottom of the image where the inlet is located near the center. The solid black line represents the measured values. Dashed with a dot are the rock outcrops only alternative, while the dashed lines represent the global overburden of 1 meter. Looking at the general trends throughout the domain, the pattern of longshore sediment transport is reproduced with some minor deviations. The peaks are present with some of the troughs that could be better represented. Looking between the two model runs, specifying 1 meter overburden reduced the longshore sediment transport both north and south of the inlet. This reduction was largely consistent between the regions north and south. In general, longshore sediment transport is overpredicted in this model with this type of forcing. The model is having difficulty reproducing longshore sediment transport rates at the southern boundary, which may be due to complex outcropping, bottom topography, or other near boundary effects. This difficulty was observed in both model runs independent of hard bottom specification type. There is a desire to move the boundary of the numerical model southward, but additional survey data is needed. A selection of observational arcs are provided in the table on the right-hand side of the panel. This is longshore sediment transport for both measured and calculated for both of the model alternatives. The primary observation here is how close the differences are between the two model runs, which is encouraging in this difficult mixed energy environment where the southern areas are influenced by the inlet. We lack any current measurements through the inlet, so we are unable to know if we are properly simulating this flow. We hope to remedy this in future field campaigns. Some conclusions and implications for numerical modeling. A general statement can be made that complete and accurate representation of the environment modeled supports calculating of coastal sediment processes. This is a good reminder for all numerical modeling investigations, and this is a very data-driven approach to simulate these processes. Calculated longshore sediment transport rates were improved by incorporating a domain-wide overburden specification, but I believe we have some room to grow here, and I'll discuss that below. The domain-wide specification improved model stability over the isolated hard bottom rock outcrops. And we can also note that the specification of hard bottom and overburden is important in this type of numerical model. We have some ongoing and future work. I'd like to repeat this analysis using the incorporation of a laboratory-derived fall velocity for the sediment transport equations. This has shown promise in other work in regards to the morphology change computation at the inlet sediment reservoirs. Some future fieldwork to further elucidate the location of hard bottom throughout the study area is also of interest, and this may support some spatially varying specification of overburden. And we'd also, as mentioned before, like to include some inlet current measurements to further refine the ebb jet. It should be noted that the inlet itself is also hard bottom. In closing, I would like to first and foremost acknowledge the committee members that helped guide this work, field participants, and previous students whose work this research builds upon. I would like to once again acknowledge the support of the Florida Institute of Technology. This work was performed within the Coastal Processes Research Group led by Dr. Zarillo. Real-time data at the Sebastian Inlet and more information about the group can be found on the CPIRG webpage. For information on the Sebastian Inlet District and their work, I've included their website below. The CMS model is developed and maintained at the Coastal Inlet Research Program, which is part of the Coastal Hydraulics Laboratory at the Engineer Research and Development Center located in Vicksburg, Mississippi. Thank you for your attention, and feel free to reach out to myself or my co-author with any questions and further discussion.